Hello, good morning, afternoon, or night, depending on where you might be around the world. On behalf of EMD International, I would like to welcome you all to today's webinar on the NORD2000 module in WindPRO. Today's presenter again will be Thomas Sorensen from EMD International. The presentation should take about 45 minutes or so, and then there will be a short question and answer session at the end, followed by a very brief summary at the very end. We ask that you please submit your questions in writing in the questions section to the bottom of your GoTo interface. You can expand the questions section by clicking on the plus symbol just to the left of the word questions, then type in your text into the window there that appears below it. Questions will be answered during the Q&A session at the end, and questions will not be accepted once the Q&A session has begun, so please submit them during the presentation. If we do not get to your question, don't worry. We're going to be sending out a link to the full Q&A summary of all questions submitted, as well as the recording of this webinar to all attendees within the next day or two. So now, without further ado, I give you to Thomas Sorensen, who will be taking you on a guided tour of the NORD2000 module in WindPRO. Please take it away, Thomas.
Thank you, Nathan. Yes, welcome to the NORD2000 webinar. This is a webinar that will introduce you to the NORD2000 calculation model in WindPRO and show you briefly how it works and what you can get out of it. The NORD2000 is a calculation model for noise modeling, which was originally developed for traffic noise. It was a few years ago validated for wind turbine noise, and we are using a calculation engine from Delta in Copenhagen, Denmark, that we call for the calculation. So you operate NORD2000 from WindPRO. It sends the data to NORD2000 and it returns the result to WindPRO again for presentation. The NORD2000 model is a very detailed model. It can handle very detailed results, detailed data, calculate on a detailed landscape, but because of that it is also a fairly heavy model, and compared to simpler models, it is mostly used for special point simulation, calculation of individual calculation points or very specific situations. Lately, the NORD2000 model has become written into the guidelines of some countries, most recently the Finnish guideline, and that means that we expect it to be used on a much more regular basis in use in the future for environmental impact studies and permits. I have actually for that reason picked a more or less random site in Finland. This is not a real site. I basically threw a dot on a map and ended up with this location, but it shows a typical landscape for a noise calculation. We have I can show you some contours here. Looks something like this, where we have a hill up here and some hill down here in the valley in between. It's not a big height difference. It's about 20-30 meters height difference here. On top of the hill, I have made a little layout 2 times 3 turbines. In this case, I have invented my own turbine. In that way, I can do anything with it I want. Called SuperWind SW 3.0, 112 meter rotor. If we go to the data for the turbine, you can see that I have noise data. You can see I have different wind speeds here, for example 8 meter per second, 7 meter per second, as third octave data. You can operate NORD2000 on octave data, 8 octave data pins, but you can also operate it with third octave data. NORD2000 starts at 25 hertz, but in WindPRO you introduce them already at 10 hertz. NORD2000 works with noise level at wind speed at hop height, which is a little different from the traditional standard at using noise level at 10 meter height. For that reason, we convert the noise level, or rather the wind speed, from 10 meter to hop height here in the turbine catalog. If you're not already done it with a turbine, you get the chance again when you start the calculation. It is very simple. You just click here, and then it will create an interpolated line at hop height. It looks something like this. Yeah, here we are. Good. If I just leave again, I have also entered a number of receptors. These are the dwellings around. They are marked by a noise receptor point. And you can see I have not put in any specifications on it. There is a demand, but in the current version, WindPRO actually doesn't check if the demand is complied with. It's merely to identify the location of the calculation point. Now, a general trick, which is not limited to NORD2000, but also generally used in decibel calculations, is that you can actually refine the location. Let's say that we have this map, and we have a receptor over here, and we're not entirely sure if we placed it on the right location. Then we can click on this icon here, which is the Google Earth synchronization. It calls up Google Earth, and in Google Earth it is quite easy to see if the location is correct. If we then zoom into the house like this, see if we can find it. There we are. Then we can see that in this case we actually made the wrong location for the house. Actually, the house is located more like over here. And so we can find exactly the right location in our noise calculation. Okay. Then we have more terrain information for, just a second, let's start with a regular decibel calculation, just for comparison. A decibel calculation is the standard calculation for noise in WindPRO. We can try and put in a ISO 9613-2 calculation, maybe set it up to finish conditions, for example, general ground attenuation at 0.4, receptor height of 4 meters, and then run the calculation. We have the 6 turbines, 7 receptors, and a noise map. And let's say we want to see not the raster, but we want to see the lines as a result layer. You can see we have these lines here. And now we run the calculation. And here we are, with noise ISO lines around the map. In this case, we can see, if we just show the legend here, that if 45 dB is our limit, we are quite safe. If 40 dB is our limit, there's a number of dwellings inside the lines. And it would be maybe worthwhile to take a closer look at these dwellings to see if this calculation is giving us the right result. So such a calculation, we can export the result with a result to file, like NSA data, copy to file, and then we can paste it into a spreadsheet here, and you can see here we have the results. I copied the results into a little table. You'll actually see that one of the receptors here gives a different result because that's the former location of that calculation point I moved. Now let's try and run the NORD2000 calculation. For the NORD2000 calculation, we need one more set of information. We need some information about the acoustic hardness of the terrain. The acoustic hardness tells WindPRO how much of the noise is attenuated by the ground, how soft or hard the ground is. The smartest way to describe this is by using an area object and then define the areas. And you can see that you can insert an area object like this and set it for NORD2000, and then you can describe different area types like this, and then you can set what kind of terrain is this. This may be a D, and you can then give it different values at different seasons. I have, however, already prepared such a map here. What I did in this case was that I went into Import, Export and Online Data, and then clicked here, and then I downloaded the Data for Wind dataset. The Data for Wind dataset is actually a roughness map in a 200 meter grid for all of Europe, and all these roughness area types correspond to a type of terrain. So I simply match each terrain types. You see, roughness 0.9 meters. I assigned a terrain hardness for this type of terrain. That's very easy and very fast, and it gives us a map with, I think, a suitable resolution in the hardness. You can see here how open land gets a higher hardness and lakes an even higher hardness, whereas whereas all the red here is forest. High roughness means high low hardness. That's a B value in this case. So now I have all the data I need for my calculation, so I can start a NORD2000 calculation. The NORD2000 calculation started here like any other calculation, so I click on it, and what I will try and do first is a simple calculation. I will calculate for a very specific situation. Let's say we have the wind is coming from the west. So wind from west. I'm calculating a point calculation, one very specific situation. As for my turbines, I will use the layer with my layout. It's my 6 turbines. For my noise receptors, I will use this receptor layer. See, it's hatched, so that's 7 noise sensitive areas. My terrain, well, I can use flat terrain, flat uniform terrain, but I can also use the terrain information I already have in my project. So I can use my line object with my high contours, and I can use for roughness my area object with roughness, and I can use the same area object for my hardness description. Roughness has not much influence on the calculation, but elevation and terrain type the hardness has. Down here I can then select which months I want to use. And that relates to that hardness description. You saw that I could use different values for different months. It could be that in winter there's snow cover and so softer terrain, whereas in the summer there will be no snow and the terrain may therefore be higher. Could be the lakes have ice in the winter and therefore very hard, but it could also be they're snow covered in winter and therefore very soft. So you can then, by selecting the months, choose the sort of hardness profile, seasonal hardness profile of your terrain. In this case, I used uniform hardness all year, so it doesn't matter which month I choose. On the wind tab, I can then tell WindPRO something about the wind regime. Now here in this first example, I will use a uniform wind speed and wind farm. That's the assumption usually made in wind modeling, that there is the same wind regime for all the wind turbines. That may not always be the case. You can have wind turbines which are located more or less exposed to the wind from any given direction. So at a particular wind direction, you will have higher wind speed at some turbines and less at other turbines. And since the source noise level is directly related to the wind speed of the turbine, you might have different source noise levels for the wind farm. But here in this initial case, we will use a uniform wind speed inside the wind farm. We are assuming that all the turbines are exposed to the same wind speed and therefore have the same source noise level. We will use a calculation wind speed at 10 meter height at 8 meters per second, which is a very standard situation. This is the situation mostly required in noise calculation. It usually is very close to the maximum noise level of turbines at hub height, not quite, but almost. And then we have the wind direction. And now we wanted to calculate wind direction from the west, so we type in 270 degrees. And we have wind speed at receiver, and let's just say 1.5 meter, which is very close to the actual height of the receivers at the dwellings. Then we have the shear. The shear tells WindPRO NORD2000 how the wind speed at 10 meter height translates to the wind speed at hub height. If you have a very low shear, you might translate the 8 meters per second to a relatively low wind speed at hub height and therefore a lower source noise level. If you have a very high shear, you may translate the 8 meters per second at 10 meter height to a much higher wind speed and thus reach probably a higher source noise level. Of course, if you're working with a high wind speeds that you already are at the nominal power or the fixed source noise level, it doesn't matter too much. But at lower wind speeds, this has quite an influence. However, most codes relate this relation between 10 meter height and hub height using a standard profile, the IEC standard profile, with a roughness length of 5 centimeters. So that is our default selection. But if you want to calculate for a specific or maybe a more real case, then you can either link to the shear you might have measured on the side and which you can find in a mates object in WindPRO, or you can put in a fixed shear, a fixed roughness class or a fixed roughness length that all comes down to the same thing. It's just different ways to describe it. As I will mention later, you can also let WASP do it, but that is a bit later. We have also the possibility to set in specific specific climatic conditions. We could calculate, for example, at 70% relative humidity and the temperature of the site. And then we have the stability parameters. The stability is an indication of whether the atmosphere is stable or unstable or neutral. In stable conditions, you will typically have cold air near the ground and warmer higher up, and so the wind doesn't mix very well. In unstable conditions, you have warmer air near the ground and colder air higher up, and so the warm air rises up and there is an increased mixing in the air. It gives a lower shear, and it also has an influence on the sound propagation. And here for the 2000 calculation, there will be that there are generally two functions of stability. The immediate influence is that it affects the atmospheric attenuation. But if you want to, you can actually affect your shear by the stability. If you go back to the shear and click here, then those stability parameters will modify the shear you're using by adding a stability component. If we show this one here, you can see that the atmospheric properties like turbulence and the stability related properties like Moon and Overcall length and temperature such as scale can be edited directly. But to make it easier, we have also defined 4 different situations here: day and night, clear sky and clouded. And you can see how it affects the stability conditions. Night and clear sky will give stable conditions. Day and clear sky will give unstable conditions. Night and clouded will give you a neutral atmosphere. A neutral atmosphere is usually the requirement in noise codes. So unless you're calculating a very specific meteorological situation, you will usually want to calculate using these settings. And then effectively you don't need to use this advanced option. Let's start the calculation. Here we go. WindPRO is calculating. In the first calculation we do, we need to set up an interpretation of the landscape. So there's a slightly added calculation time here to the first calculation, but that should be only a few seconds. And there we are. So this calculation took us 27 seconds. The report print, let's see, we have first on the front page the calculation settings for our specific calculation. You can see down here we have the 6 turbines, our 6 super wind SW 3.0 turbines. We can see here that the wind speed at hop height is 11.4 meters per second. So that's the wind speed WindPRO uses to look up into the hop height source noise level graph to find the source noise level at hop height, which is then 106.4 decibel. We have down here the result at each receptor. And in the following pages we have the assumptions for calculation. Here you can see the source noise level, and you can see this is the hop height table, not the 10 meter table but the hop height table. And we have all the receptors defined, and then for each receptor we have the source noise data from a turbine, and we have the resulting octave band distribution from each turbine at each receptor. And finally we have a map. WindPRO does not draw any noise isolines from the NORD2000 calculation, at least it doesn't yet. We're working on introducing it in WindPRO 3.0 and hope it works out. The problem is that the calculations are relatively slow, and that means that you have the risk, if you have a large wind farm, many receptors, but most importantly a very dense hardness map, that the calculation will take extraordinarily long time. It's something we're working on, and hopefully we will be able to speed up the calculation enough that we can include noise isolines in WindPRO 3.0. But so far, the map would just give you the location of the turbines and the location of the receptors. We can export this result to file naturally. Of the interesting results is this third octave data. If we copy this to clipboard, for example, you can see here, then we actually get a result out in third octave. And the really interesting thing about it is that out here in the end we have a resulting noise, including the resulting third octave result here. And that means that you can actually use this result for low frequency calculations. I should mention that these data are already A-weighted, so you need to do some maneuvering around if you want to, for example, use C-weighting and so on. Okay, we can also take the standard result out, data to file, and copy that to our table here, and I've done that here. And what you can then see is that the result is quite different from our ISO standard result. You can see that for many of these receptors, the noise level is significantly less than NORD2000. And you might wonder why that is. There are three main explanations why you get a lower result. The first one is that the turbines are located on a hill and the receptors are down below, and there's some effect from this terrain. That means that you get, which is not included in an ISO standard calculation, which just assumes a flat terrain. Secondly, we are using a hardness map, and the hardness tells us that most of this side is forest, and forest is very soft, and so it absorbs the noise, and therefore we will get a lower value than the ISO calculation. The ISO calculation we used 0.4, and this forest would probably be closer to a hardness of 1. Thirdly, we calculated for western wind direction. If you just switch off the arrows again, you can see that if wind is from the west, these receptors here will be upwind from the turbines. And that means that you will get less noise from the wind farm than if you are down here behind the turbines. Let's see, this one here is the second one, and this one here is second to last. If we look at the table here, we can see that that second one, which is upwind, has only 25 dB compared to the ISO calculation, whereas the second to last is actually quite close to the result from the ISO calculation. What if we turn it around? What if we make a calculation from the east? Let's try and do that. Then we just clone. We can then say wind from east. We use exactly the same setup all the way through, except for here. Here we choose 90 degrees instead. And start. And now we are again calling NORD2000. And we can see that since we did not need to recalculate terrain again, we are down to 5 seconds, which is actually pretty fast. Now our results are a little bit different. We don't need to look at the result. I copy them out to spreadsheet, and we get this table here. You can see that for some of the receptors it doesn't really matter. A, for example, which is located here to the north, it doesn't matter if it's from east or west. The turbines are to the south. So the noise level is quite similar. But For the B, which is located here west of the wind farm, the difference is big. Here we get now 35 dB, whereas we before got 25 dB. And also the other receptors here in front of the turbine get a much higher result now that the wind is from the east. Of course, the F, which is actually the east of the wind farm, they now get a lower noise level than before. So we have a little problem here. We want to calculate a downwind noise level from our turbines. But no matter what we choose, it is not downwind. For some of the receptors, the turbines will actually be upwind. What we can do is that we can try and calculate all the different directions, and then we can take the result out that gives you the highest noise level. So what would be the noise level from the turbine in the wind direction which is highest? You can see, of course, if you look at only this receptor here, for this receptor, wind speed from this direction will give the highest value. But when the wind direction comes from this direction, these turbines is actually upwind, and they will contribute less. So therefore, the wind direction that combines the noise level from the different turbines at each receptor and give the highest value might not be quite obvious. Let's try and make such a calculation. I will copy this calculation again, and this time I will say most downwind situation. Now I will, instead of calculating for a specific situation, I will make this speed direction analysis using the same settings except for the wind table here. In this situation, I will calculate in a range. I will use just the same wind direction, but I will use a number of different, same wind speed, just 8 meters per second, but I will calculate a range of wind directions, 12 wind directions to be specific. Sorry, 30 degrees instead. So I get 12 wind directions at 8 meters per second, 8 to 8, step 1. So, yes, and now run the calculation again. Now this calculation, of course, takes more time. It takes exactly 12 times longer because we have to repeat this calculation 12 times for each turbine receptor pair. That is the price of doing this. Of course, if you also want to calculate this for a number of wind speeds, we add another dimension to the calculation matrix, and then things starts getting really slow. But we should have a result very shortly. Yeah, it's almost there. You can see 98%. There we are. Then we can show the result. Preview. Now we lose some information here on the front because we do not have a specific wind speed or noise level, because we are looking in a range of parameters, and therefore it's not unambiguous what we are using. We get a table here, a result with the different maximum noise level. These are the noise levels at each receptor in the wind direction when they get the highest noise level. And that direction might be different from each turbine. If you look here at turbine number A, which direction has the highest noise level, we can see 42 dB here in these northern directions gives you the highest noise level. Receptor B, you can see there's a huge difference. Here from 270 degrees we get a very low noise level, but the highest level would be something like 35.8, looks like, and so on. And so for each receptor the highest noise level is picked, the wind direction of the highest noise level. We have again the assumptions, and then here in detail you can see now we have a lot of calculations for each receptor, because we are doing 12 calculations now for each one, and you can see that's a ton of data. If we just quickly move forward here, you can then see we get this new sheet. We get a wind speed direction analysis, and here you can then see how the wind direction, the noise level is a function of wind direction, both in this sort of diagram and a radar diagram. And we can get that for every receptor. Now I have copied those results into my little spreadsheet, and I get this result. And you can see that we are getting a higher noise level now than we did before, and we are actually approaching our ISO calculation. ISO calculation is using the downwind situation, and so are we as well now, or at least most downwind. There's still some difference, but it's not unrealistic anymore. So let's look at a last situation here. I mentioned earlier that we are making the assumption that noise level is uniform within the wind farm. In reality it is not. There are two particular things that gives you different wind speeds inside the wind farm. One thing is that the turbines may be exposed differently to the wind in different directions. The hills and also roughness, but particularly hills, gives you different speed ups in different directions, and the turbines are differently exposed to it. What might give a high wind speed at one direction might in another direction give a lower wind speed for a given turbine compared to the others. And we can actually model that. The other thing is that the wakes of the turbines may give a different wind speed at these turbines. The logical conclusion to that would be that the turbines will then have a different source noise level. That is still up for discussion, because a turbine in the wake of another turbine will also get a higher turbulence level. And will that increased turbulence give a higher noise level? And will that turbulence, that increase in noise level, actually overrule the decrease in wind speed? That is not entirely settled yet, and therefore we are a bit reluctant to include that effect. We can, but it's a little more on an experimental basis. If we go back to our calculation, let's say we can take this most downwind situation and clone it. We can include most downwind situation and wind speed difference. If you wanted to calculate with a wake effect, we can include a WIW file, wind speed inside wind farms. It's a particular file you can create in a part calculation that will tell WindPRO that if you have a specific free wind speed, what would be the wind speed at each turbine taking into account the wake, and then use that to give the relation between the turbines. It's not very easy to do, and it's mainly because we think it's probably a poor idea. We are not certain that that decrease in wind speed will result in lower noise levels. It might actually go the other way. But the different exposure you can do in a standard calculation. In that case, we move on to wind, and then we calculate wind speed differences inside wind farm. The problem with doing this is that you need a reference location because we want to calculate in a specific wind speed at a specific location. But where is that location? It's a big difference whether you choose a very exposed turbine to a less exposed turbine, or whether you choose a turbine to a receptor, or maybe a meteorological tower. Now, in my situation, I have simulated a local wind mast on the site, and I will then choose that for my calculation. I have here chosen that. Yeah, I'm a little ahead of myself, so I'll just cancel this calculation for now. Go back to the map and show you this little object here. This is a site data object which is generally used in the noise calculations, in the energy calculations. Inside this object we have a roughness description, and we have a high contour description. You can see here is these two files. The roughness description is simply an export from the area object into roughness lines, which you can see here. So let's go back to our calculation here again. Now I just have to redo this. Most downwind situation and wind speed differences. Here on my terrain, on my wind, I will use calculated wind speed difference. I will use my mast as my reference location at 10 meter height, 8 meter per second, 0 to 330 degrees. And then my description of the terrain for my WASP model that will model the difference from my reference location and out to each turbine will be described by the site data object I have here for my local wind data. I could then say that I will, well, you can see here that my profile will now be the WASP share. Now it's WASP that calculates the difference in wind speed from my reference location height to hop height. If I have chosen a height here, which was the hop height, 100 meters, then WASP will only transform horizontally from that point at 100 meters out to each location of the turbines at 100 meters. But now also the share is modeled by WASP. And so we can calculate. First it runs the WASP calculation, and then it runs the NORD2000 calculation. Yeah, it takes a minute or two to calculate. You can see that the other calculation took 0.56 seconds. So this calculation will take something very similar. You can see that it's shown there, 61%. And here we then have the results. If we look at the report, we can see that we have something very similar to the upper and downs, except that now we have a terrain, a WASP to calculate the wind speeds. We can also see that this looks very similar, and over here on the results, we now have something different. The wind speed at hop height is different. It's quite a bit higher than before because this is the forested side with a high shear, and therefore we had high wind speeds at hop height. However, it results in basically the same noise level because at this level of wind speed we are on the flat part of the noise curve. Okay, and the different tables here looks very similar to before, except that now because we have terrain effects, we get somewhat more difference from each direction. Okay, we can copy the result out into our spreadsheet. Here we are. And now we have the wind speed in. Because we are reaching a higher wind speed because of the higher shear that we actually have on the side, we get some higher noise levels. We are still below or very close to the ISO standard, so even that fails to exclude to get a higher value. We are still conservative with our ISO model in this situation. Yes. These are basically the calculations you can do right now in a 2000. We are working on a number of improvements for a 2000 for the next version, and while it may be too early to actually promise things, I can tell you that we are working on noise ISO lines. We are working on a low frequency calculation output so that you get an actual report for it, and we are also working on a statistical model that tries to give you the average noise and different probability levels of noise at the receptor. Mind you, this is a very tricky business because the wind speed distribution is actually only part of it. You have a lot of variety in the atmosphere and in other ground parameters, for example, that may change conditions over time. But it's a challenge. Anyway, those improvements should be out in WindPRO 2.3. Sorry, 3.0. What I've shown you right now is currently available in 2.9, and it is available for sale from our website now. Okay, Nathan, back to you.
Okay, thank you very much, Thomas. Thank you for all of your questions. That concludes the presentation portion of the program. We will get to the Q&A portion here very shortly. We'll give Thomas a chance here to go through all of your questions and select a few to be answered. But again, if we do not get to your question, then don't worry. We're going to have available a Q&A summary of all questions submitted, and we will have that available within the next 24 hours. For the meantime, I would like to let you know ways you can contact us for more information about the NORD2000 module or how to order it. You can read more on the NORD2000 module at our knowledge base site that you see there, the top link on your screen. That is also where we'll keep this webinar and our previous webinars and the Q&A summaries for them. You can order NORD2000 either on our website there under ordering, or you can contact our sales department at the sales@emd.dk or the telephone number you see there during standard business hours for Denmark. If you have any technical questions, you can submit them to support@emd.dk, and that is our tech support direct email. So I think now I will give it back over to Thomas to answer a few questions. So please take it away again, Thomas.
Thank you, Nathan. Yes, we have received a number of questions, and I will answer them very briefly here, and you will get a slightly more detailed answer in the material we'll send to you here after the webinar. The first question is if interpolation from 10 meter up to hop height is done with a standard roughness length of 5 centimeters. And yes, that is the case as the default value. But you can use other shears in the NORD2000. In the turbine catalog, when we create those source noise levels at hop height, we are using this 5 centimeter roughness value to change the wind speeds at 10 meter height to hop height, because that is how it is defined in the IC standard. The next question is if you can use GIS Corinne land use data to specify acoustic hardness. If the data are available as shapefiles, then the answer is yes. WindPRO needs closed shapefiles areas. If you can get the data as closed areas in shapefiles, you can use them in WindPRO. I should mention at this point that the detailedness of these data has a huge impact on calculation times. In an experiment I made, I found out that an actual GIS model of a site like the one I showed you from the local planning office would take 10 times longer to use than the 200 meter grid I used for my calculation. So it's worthwhile to optimize on that account. Then we have a question if it is a 2000 thing that sound power level is related to wind speed at hop height. And we do that because we want to be able to model the wind speed difference inside the wind farm. If you just use the 10 meter height data, you are also tied to this IEC profile. But if you work with hop height noise levels, then you have much more flexibility in looking at the actual wind conditions at the site, both in terms of wind speed levels and in terms of the differences inside the wind farm. So we think it's an advantage, plus that the standards are moving towards noise level at hop height wind speeds. Then there's a question if NORD2000, what is NORD2000 worst case? And worst case is a tricky question. I already showed you how different wind directions can be combined to a worst case situation. But worst case can also be different shears. When you have an extremely high shear, you will get very high wind speeds at hop height and therefore high source noise levels. But you don't need to put a particular high shear. If you choose, for example, 10 meter per second or 11 meter per second as your 10 meter height wind speed, you will hit the flat level of the noise curve on your turbine, and that is the highest source level, noise level for the turbines. There are also climatic parameters that can be changed and give higher values, and you can modify those. But you should be aware that most codes uses fixed values for those atmospheric parameters. So you may want to keep them in a fixed setting. The Swedish codes are different in WindPRO only in the sense that we lock a number of these climatic parameters to the value defined in the Swedish guidelines. Otherwise, the calculation is very similar to what I showed you as the worst wind direction calculation at 8 meters per second. Then we have a question if it's possible to calculate year average values in NORD2000. Not in WindPRO 2.9, but in 3.0 we are introducing a model where you can apply the Weibull distribution for your site to calculate the how often you have different wind speeds and different directions, and therefore different source noise levels for the turbines, and that gives you a probability model for how often you get different noise levels at the receptor. The problem there, of course, is that that only looks at the wind speed and direction. There are also differences in ground attenuation and climatic parameters that may cause differences. So it would so far only be a guideline value. That's the questions I have answered here. We will give you a complete overview of the answers in the materials sent around after this webinar. Thank you very much, and back to you, Nathan.
Thanks a lot, Thomas. And that is time for today's webinar on WindPRO's NORD2000. When the webinar ends, a close button will pop up in your go-to interface. Please press that button and the survey will then open in your web browser. It is a very, very short survey and should not take literally more than about 30 seconds of your time, and we would greatly appreciate it. You will also have the ability at the end of the survey to request a limited time trial license for testing the NORD2000 module. I hope you've enjoyed the webinar, and please look forward to some more information from us within the next 24 hours, including the link to the video of this presentation and the Q&A summary. So again, have a good day, evening, or night, depending on where you might be in the world, and thanks for your time and attention.